In mathematics, the classical groups are defined as the special linear groups over the rails R, the complex numbers C and the quaternions H, together with special automorphism groups of symmetric or skew-symmetric bilinear forms and Hermitian or skew-Hermitian sesquilinear forms defined on real, complex and quaternionic finite-dimensional vector spaces. Of these, the complex classical Lie groups are four infinite families of Lie groups that, together with the exceptional groups, exhaust the classification of simple Lie groups. The compact classical groups of compact real forms of the complex classical groups. The finite analogues of the classical groups are the classical groups of Lie type. The term classical group was coined by Hermann Weyl, it being the title of his 1939 monograph The Classical Groups. The classical groups form the deepest and most useful part of the subject of linear Lie groups. Most types of classical groups find application in classical and modern physics. A few examples are the following. The rotation group SO is a symmetry of Euclidean space and all fundamental laws of physics. The Lorentz group O is a symmetry group of space-time of special relativity. The special unitary group SU is the symmetry group of quantum chromodynamics, and the symplectic group SP finds application in Hamiltonian mechanics and quantum mechanical versions of it. The classical groups. The classical groups are exactly the general linear groups over R, C and H, together with the automorphism groups of non-degenerate forms discussed below. These groups are usually additionally restricted to the subgroups whose elements have determinant 1. The classical groups, with the determinant 1 condition, are listed in the table below. In the sequel, the determinant 1 condition is not used consistently in the interest of greater generality. The complex classical groups are SL, SO and SP. A group is complex according to whether its Lie algebra is complex. The real classical groups refers to all of the classical groups since any Lie algebra is a real algebra. The compact classical groups are the compact real forms of the complex classical groups. These are, in turn, SU, SO and SP. One characterization of the compact real form is in terms of the Lie algebra G. If G equals U plus U, the complexification of U, then if the connected group K generated by exp. XU is a compact, K is a compact real form. The classical groups can uniformly be characterized in a different way using real forms. The classical groups are the following. The complex linear algebraic groups SL, SO, and SP together with their real forms. For instance, SO is a real form of SO, SU is a real form of SL, and SL is a real form of SO. Without the determinant 1 condition, replace the special linear groups with the corresponding general linear groups in the characterization. The algebraic groups in question are Lie groups, but the algebraic qualifier is needed to get the right notion of real form. Bilinear and sesquilinear forms. The classical groups are defined in terms of forms defined on Rn, Cn, and Hn, where R and C are the fields of the real and complex numbers. The quaternions H do not constitute a field because multiplication does not commute. They form a division ring or a skew field or non-commutative field. However, it is still possible to define matrix quaternionic groups. For this reason, a vector space V is allowed to be defined over R, C, as well as H below. In the case of H, V is a right vector space to make possible the representation of the group action as matrix multiplication from the left. Just as for R and C, a form phi V times Vf on some finite-dimensional right vector space over F equals R, C, or H is bilinear if it is called sesquilinear if these conventions are chosen because they work in all cases considered. An automorphism of phi is a map alpha in the set of linear operators on V such that the set of all automorphisms of phi form a group. It is called the Automorphism Group of phi, denoted AUT. This leads to a preliminary definition of a classical group. A classical group is a group that preserves a bilinear or sesquilinear form on finite-dimensional vector spaces over R, C or H. This definition has shortcomings because there is some unnecessary redundancy. In the case of F equals R, bilinear is equivalent to sesquilinear. In the case of F equals H, there are no non-zero bilinear forms. Symmetric, skew-symmetric, Hermitian, and skew-Hermitian forms. A form is symmetric if it is skew-symmetric if it is Hermitian if finally it is skew-Hermitian if a bilinear form phi is uniquely a sum of a symmetric form and a skew-symmetric form. A transformation preserving phi preserves both parts separately. The groups preserving symmetric and skew-symmetric forms can thus be studied separately. The same applies, mutatis mutandis, to Hermitian and skew-Hermitian forms. For this reason, for the purposes of classification, only purely symmetric, skew-symmetric, Hermitian, or skew-Hermitian forms are considered. The normal forms of the forms correspond to specific suitable choices of bases. These are bases giving the following normal forms in coordinates. The J in the skew-Hermitian form is the third basis element in the basis for H. Proof of existence of these bases and Sylvester's law of inertia, the independence of the number of plus and minus signs P and Q in the symmetric and Hermitian forms, as well as the presence or absence of the fields in each expression, can be found in Rossmann or Goodman and Wallach. The pair, and sometimes P minus Q, is called the signature of the form. Explanation of occurrence of the fields R, C, H. There are no non-trivial bilinear forms over H. In the symmetric bilinear case, only forms over R have a signature. In other words, a complex bilinear form with signature can, by a change of basis, be reduced to a form where all signs are plus in the above expression, whereas this is impossible in the real case, in which P minus Q is independent of the basis when put into this form. However, Hermitian forms have basis-independent signature in both the complex and the quaternionic case. A skew-Hermitian form on a complex vector space is rendered Hermitian by multiplication by I, so in this case, only H is interesting. Automorphism groups. The first section presents the general framework. The other sections exhaust the qualitatively different cases that arise as automorphism groups of bilinear and sesquilinear forms on finite-dimensional vector spaces over R, C and H. AUT. The automorphism group assume that phi is a non-degenerate form on a finite-dimensional vector space V over R, C or H. The automorphism group is defined based on condition, as every AMN has an adjoint A phi with respect to phi defined by using this definition in condition. The automorphism group is seen to be given by fix a basis for V. In terms of this basis, put where xi I, A to j are the components of X. This is appropriate for the bilinear forms. Sesquilinear forms have similar expressions and are treated separately later. In matrix notation one finds and from where phi is the matrix. The non-degeneracy condition means precisely that phi is invertible, so the adjoint always exists. AUT expressed with this becomes the Lie algebra. AUT of the automorphism groups can be written down immediately. Abstractly, XAUT if and only if for all t corresponding to the condition in under the exponential mapping of Lie algebras, so that or in a basis as is seen using the power series expansion of the exponential mapping and the linearity of the involved operations. Conversely, suppose that XAUT. Then, using the above result, phi equals phi. Thus the Lie algebra can be characterized without reference to a basis, or the adjoint, as the normal form for phi will be given for each classical group below. From that normal form, the matrix phi can be read off directly. Consequently, expressions for the adjoint in the Lie algebras can be obtained using formulas, and this is demonstrated below in most of the non-trivial cases. bilinear case when the form is symmetric, AUT is called O. When it is skew-symmetric then AUT is called SP. This applies to the real and the complex cases. The quaternionic case is empty since no non-zero bilinear forms exists on quaternionic vector spaces. Real case. The real case breaks up into two cases, the symmetric and the anti-symmetric forms that should be treated separately. O and O, the orthogonal groups if phi is symmetric and the vector space is real. A basis may be chosen so that the number of plus and minus signs are independent of the particular basis. In the case V equals Rn1 writes O equals O where P is the number of plus signs and Q is the number of minus signs, P plus Q equals N. If Q equals 0 the notation is O. The matrix phi is in this case after reordering the basis if necessary. The adjoint operation then becomes which reduces to the usual transpose when P or Q is 0. The Lie algebra is found using equation and a suitable ansatz, and the group according to is given by the groups O and O are isomorphic through the map. For example, the Lie algebra of the Lorentz group could be written as naturally. It is possible to rearrange so that the Q block is the upper left. Here the time component end up as the fourth coordinate in a physical interpretation, and not the first as may be more common. SP, the real symplectic group if phi is skew-symmetric and the vector space is real. There is a basis giving where n equals 2 meters. For AUT1 writes SP equals SP in case V equals Rn equals R2 meters 1 writes SP or SP. From the normal form one reads off by making the ansatz where x, y, z, w are m-dimensional matrices and considering. One finds the Lie algebra of SP, and the group is given by complex case. Like in the real case, there are two cases, the symmetric and the anti-symmetric case, that each yield a family of classical groups. O, the complex orthogonal group if case phi is symmetric and the vector space is complex. A basis with only plus signs can be used. The automorphism group is in the case of E equals Cn called O. The Lie algebra is simply a special case of that for O, and the group is given by it in terms of classification of simple Lie algebras. The SO are split into two classes, those with n odd with root system Bn and n even with root system Dn. SP, the complex symplectic group for phi skew-symmetric and the vector space complex. The same formula applies as in the real case. For AUT1 writes SP equals SP in case V equals n equals 2 meters 1 writes SP or SP. The Lie algebra parallels that of SP, and the group is given by sesquilinear case. In the sequilinear case, one makes a slightly different ansatz for the form in terms of a basis. The other expressions that get modified are the real case, of course, provides nothing new. The complex and the quaternionic case will be considered below. Complex case from a qualitative point of view. Consideration of skew-Hermitian forms provide no new groups. Multiplication by I renders a skew-Hermitian form Hermitian, and vice versa. Thus only the Hermitian case needs to be considered. The automorphism group is denoted U, or, in the case of E equals Cn. If Q equals 0 the notation is U. In this case, phi takes the form and the Lie algebra is given by the group is given by quaternionic case. The space Hn is considered as a right vector space over H. This way, A equals H for a quaternion H, a quaternion column vector V and quaternion matrix A. If Hn was a left vector space over H, then matrix multiplication from the right on row vectors would be required to maintain linearity. This does not correspond to the usual linear operation of a group on a vector space when a basis is given, which is matrix multiplication from the left on column vectors. Thus V is henceforth a right vector space over H. Even so, care must be taken due to the non-commutative nature of H. The details are skipped because complex representations will be used. When dealing with quaternionic groups, it is convenient to represent quaternions using complex 2 times 2 matrices. With this representation, Quaternionic multiplication becomes matrix multiplication, and quaternionic conjugation becomes taking the Hermitian adjoint. Moreover, if a quaternion according to the complex encoding Q equals x plus jy is given as a column vector T, then multiplication from the left by a matrix representation of a quaternion produces a new column vector representing the correct quaternion. This representation differs slightly from a more common representation found in the quaternion article. The more common convention would force multiplication from the right on a row matrix to achieve the same thing. Incidentally, the representation above makes it clear that the group of unit quaternions is isomorphic to SU. Quaternionic n times n matrices can, by obvious extension, be represented by 2n times 2n block matrices of complex numbers. If one agrees to represent a quaternionic n times 1 column vector by a 2n times 1 column vector with complex numbers according to the encoding of above, with the upper n numbers being the alpha I and the lower n the beta I, then a quaternionic n times n matrix becomes a complex 2n times 2n matrix exactly of the form given above, but now with alpha and beta n times n matrices. More formally, a matrix TGL has the form displayed in if and only if JNT equals TJN. With these identifications, the space MN_M2N is a real algebra, but it is not a complex subspace of M2N. Multiplication by I and Mn using entry-wise quaternionic multiplication and then mapping to the image in M2N yields a different result than multiplying entry-wise by I directly in M2N. The quaternionic multiplication rules give I equals plus j where the new x and y are inside the parentheses. The action of the quaternionic matrices on quaternionic vectors is now represented by complex quantities, but otherwise it is the same as for ordinary matrices and vectors. The quaternionic groups are thus embedded in M2N where n is the dimension of the quaternionic matrices. The determinant of a quaternionic matrix is defined in this representation as being the ordinary complex determinant of its representative matrix. The non-commutative nature of quaternionic multiplication would, in the quaternionic representation of matrices, be ambiguous. The way Mn is embedded in M2N is not unique, but all such embeddings are related through G-1 GGL for AO, leaving the determinant unaffected. The name of SL in this complex guise is SU. As opposed to in the case of C, both the Hermitian and the skew-Hermitian case bring in something new when H is considered, so these cases are considered separately. GL and SL under the identification above, its Lie algebra GL is the set of all matrices in the image of the mapping MN_M2N of above. The quaternionic special linear group is given by where the determinant is taken on the matrices in C2N. The Lie algebra is SP. The quaternionic unitary group as above in the complex case. The normal form is and the number of plus signs is independent of basis. When V equals Hn with this form, SP equals SP. The reason for the notation is that the group can be represented, using the above prescription, as a subgroup of SP preserving a complex Hermitian form of signature if P or Q equals 0. The group is denoted U. It is sometimes called the hyperunitary group in quaternionic notation, meaning that quaternionic matrices of the form will satisfy. See the section about U. Caution needs to be exercised when dealing with quaternionic matrix multiplication. But here only I and I are involved and these commute with every quaternion matrix. Now apply prescription to each block, and the relations in will be satisfied if the Lie algebra becomes the group as given by returning to the normal form of phi for SP. Make the substitutions WU plus JV and ZX plus JY with U, V, X, Y, CN, then viewed as AH-valued form on C2N. Thus the elements of SP, viewed as linear transformations of C2N, preserve both a Hermitian form of signature and a non-degenerate skew-symmetric form. Both forms take purely complex values, and due to the prefactor of J of the second form, they are separately conserved. This means that, and this explains both the name of the group and the notation, O equals O quaternionic orthogonal group. The normal form for a skew-Hermitian form is given by where J is the third basis quaternion in the ordered listing. In this case, AUTE equals O may be realized using the complex matrix encoding of above as a subgroup of O, which preserves a non-degenerate complex skew-Hermitian form of signature. From the normal form one sees that in quaternionic notation, and from follows that for VO, now put according to prescription. The same prescription yields for phi. Now the last condition in complex notation reads the Lie algebra becomes, and the group is given by the group, so can be characterized as where the map theta GL is defined by G minus J2N J2N. Also, the form determining the group can be viewed as AH-valued form on C2N. Make the substitutions XW1 plus IW2 and YZ1 plus is2 in the expression for the form. Then the form phi1 is Hermitian of signature. The signature is made evident by a change of basis from 2 square root 2, where E, F are the first and last n basis vectors respectively. The second form, phi2, is symmetric positive definite. Thus, due to the factor J, O preserves both separately, and it may be concluded that, and the notation O is explained.